It may be the best way to understand the principles of quantum mechanics that define quantum computing is to build a quantum computer. In this part, we'll try to build one from scratch. In order to do so, we need to go to a lab and carry out a little experiment. This experiment consists of two stages. Stage 1, preparation, and stage 2, checking. In stage 1, we take an electron and give it an angle. In stage 2, we check the angle and the quantum state of this electron. Well, what does it mean to give an electron an angle? That leads us to the concept of quantum spin. Every particle, including electrons, have angular momentum. But angular momentum is constant because if we raise or lower the value of angular momentum, we will obtain a completely different particle. But what we can change is the direction in which the particle rotates in space, and that's called spin. The spin for an electron is quantized, like many of its characteristics. That means it has a maximum value and a minimum value, and certain values in between. That's all along a certain axis, which is now z-axis. We say we can raise the value of spin along the z-axis for an electron by making the direction of rotation get closer to the direction of z-axis. According to the laws of quantum mechanics, we can represent the spin as a quantum operator. A quantum operator acts on a wave function or quantum state to change it in a certain way. Let's now invent an operator and call it L+. L+ will act on the spin of the electron and raise it in the z direction. We can write the relation for L+ in terms of Lx and Ly, which means we can write the raising operator in terms of the spin along the x-axis and y-axis. In a similar fashion, we can lower the spin along the z-axis by inventing the lowering operator L-, which can be represented in terms of the spin along the x-axis and y-axis. One last thing in quantum mechanics before I go back to the lab. The commutation relation for two different components of the spin, Lx and Ly, can be written in terms of the third component, Lz. Let's go back to the first stage of our experiment and take an electron and put it inside a magnetic field as shown in this picture. We can rotate the magnetic field in any direction we want, given this electron a certain angle. This is how we prepare the angle of the electron in stage 1. In stage 2, we take the same electron to check the direction of this electron. It will either be up or down. In the second stage, if the electron takes the down position, it will emit electromagnetic radiation with certain energy, the same energy that the electron requires to transfer from the down position to the up position. Now, the first case, we take the electron and prepare it in 45 degrees. When we check this electron in the second stage, we find 70% of the cases the electron turned up, and 30% of the cases the electron turned down. When we make the electron horizontal in the first stage, that means give it an angle of 0, and then check the direction in the second stage, we found that 50% of all cases the electron turned up, and 50% of all cases the electron turned down and emitted electromagnetic radiation. Now, when we gave the electron an angle of 45 degrees facing down and put it in the second stage, we found out that the electron turned up only in 30% of all cases, and it turned down in 70% of all cases. What we conclude from this experiment is that we cannot predict which way the electron will turn when we put it in the second stage, but the way we prepared in the first stage, that means the angle that we gave to the electron, it will affect the probability distribution that we find in the second stage. That means regardless to the way we prepared the electron in the first stage, in the second stage the electron was in a superposition of two quantum states. up and down. And this is the concept of wave function in quantum mechanics. Wave function, psi, is a superposition of all possible states. In this case, we have an electron. It can only turn up or down. Notice the coefficients associated with each quantum state, alpha and beta. Alpha and beta in the wave function formula, they're complex numbers, and they represent the probability for each quantum state to occur. So we can use the wave function to calculate the probability for each quantum state to be measured simply by taking the coefficient linked with that quantum state and square it, alpha squared and beta squared. Why do we square the coefficients in the wave function formula to get the probability for each quantum state to occur? The answer is like that. Alpha and beta, they're both complex numbers. Each complex number has its own complex conjugate. If we multiply alpha with its complex conjugate and multiply beta with its complex conjugate and then add all the results up, we get 1. 1 means all the possible outcome. In that case, we have alpha and alpha conjugates represent part of all the possible outcome. And alpha multiplied by alpha conjugates, we can represent this process by just squaring the complex number and finding the square of the length for that complex number. Back to our experiment. Remember when we prepared the electron in the first stage in a horizontal way, we gave it an angle of 0 along the z-axis. And then we got 50% chances the electron turns up and 50% chances the electron turns down. We wrote the superposition like this. 1 over 2, the quantum state, the electron turns up along the z-axis, plus 1 over 2, the electron turns down along the z-axis. Now notice the 0 angle along the z-axis, it's the same as the maximum spin along the x-axis. So now we have a relation that link the spin along the x-axis with the spin along the z-axis. The maximum spin for an electron along the x-axis is equal to the superposition of 1 over 2 quantum state, an electron having a maximum spin along the z-axis plus 1 over 2 quantum state, an electron having a minimum spin along the z-axis. In a similar way, we can say the minimum spin for an electron along the x-axis is a superposition for the spin of the electron along the z-axis, but with minus instead of plus, like this. So we can write the maximum spin for an electron along the x-axis in terms of the electron spin along the z-axis, as shown in the superposition. Let's now ignore the first stage of the experiment and concentrate on the second stage. How can we manipulate the magnetic field in such a way we can turn or switch the maximum spin for an electron along the x-axis to a minimum spin along the x-axis? When we put the electron in the second stage, there will be an electromagnetic interaction between the electron and the magnetic field itself. This electromagnetic interaction will affect the energy of that electron. Now, the strength of the magnetic field in the second stage along the z-axis, we can call it B of z. And it's equal to B0, B0 is a constant, plus beta of z. Beta of z is the gradient of the magnetic field along the z-axis, which means the strength of the magnetic field gets stronger as we approach the direction z. We also have the energy for the electron given in this relation. E electron is equal to S vector B vector. S vector is the momentum of spin for the electron along the z-axis. B vector is the strength of the magnetic field of the second stage along the z-axis, which we just expressed in this mathematical relation. The secret to manipulate energy in quantum mechanics is through the Schrodinger equation. The Schrodinger equation describes the change of energy when we advance in time. Let's take a small example of an electron with 3 discrete energy levels. low energy level, medium energy level, and high energy level. Now we can write the wave function, which is the superposition of all three quantum states as shown here. But remember, we still need coefficients to describe the probability for each quantum state to be measured. So we take e to the power of I phi. Phi is the phase of the complex number, which is equal to E, the energy of that quantum state, multiplied by T, the time we advanced, over h bar, the constant. And this is the simplest form for the Schrodinger equation. The final wave function is equal to the initial wave function multiplied by the way we advanced in time, and represented now in this energy operator, E to the power of I et over h bar. H bar is constant. And we know from particle physics that the energy E is equal to omega multiplied by h bar, Planck constant. So we can have another simple form for the Schrodinger equation, this time written by the terms of omega t instead of et over h bar. The idea now is to build a device in the lab that allows us to switch the maximum spin of the electron to the minimum spin, and vice versa. We all saw in the second stage of the experiment the magnetic field can affect the energy of the electron. Also, we found that the Schrodinger equation can represent the change of the electron energy when we advance in time. Now, we need to correlate these two concepts with each other to come up with a device that can use the Schrodinger equation to manipulate the energy of the electron, thus switching the spin from maximum value to minimum value. The Schrodinger equation for an electron having a maximum spin along the x-axis is a quantum superposition for the same electron having a maximum and minimum spin along the z-axis, as we found. Also, we have the coefficients e to the power I omega t. Omega is equal to energy over h bar. Omega is the frequency of the electron. The frequency omega, on the other hand, is equal to c. C is a constant, and multiplied by bc, the strength of the magnetic field along the z-axis in the second stage. And this is something we can adjust in the lab. We can lower and raise the strength of the magnetic field along the z-axis. So now we can change this coefficient e to the power minus I omega t to be equal -1 by running the magnetic field for a certain amount of time t and adjusting the omega by adjusting the strength of the magnetic field along the z direction, so that we get e to the power minus I 2 pi, which is equal to -1. With the change in signs of the superposition describing the spin along the z-axis, we get the Schrodinger equation for the minimum spin along the x-axis. Now, if we consider the maximum spin for the electron along the x-axis to be a qubit 1, and the minimum spin for the electron along the x-axis to be the qubit 0, we just found a way to use the magnetic field and manipulate the strength of the magnetic field to switch this qubit from 1 to 0 and 0 to 1. We did that by manipulating the strength of the magnetic field along the z direction, so that we can change the maximum spin for the electron along the x direction to the minimum spin. This is the idea behind the quantum computing, Schrodinger equation, and building a device that can control magnetic fields, so we can change the spin of the electron from maximum value to minimum value